using fusion. And then hydrogen's up here at atomic chart, helium's over here. So you divide your atomic chart down the middle. Some are metals and some are non-metals. I don't want to get heavy into that. As long as you know hydrogen is up here and helium's there, then all these elements underneath come by the sun continuing to hit helium. And we start adding electrons to belts, we start adding them different places. So one thing we talked about in the past is the various in atoms. So draw a hydrogen. Okay, you have a neutron, a proton, and a circle around, that's the nucleus. Proton P. It's positive, neutron is nothing.
I don't know
zero.
what you want me to draw.
Did you put a plus sign?
I don't know what you want me to draw.
A plus sign for a proton. Not a photon, a proton, okay. Well, those are your electrons. Now you only have one electron for hydrogen, right? It's the simplest atom there is.
I don't know what this is.
He wants to
Yeah, I know, but I don't know what it is. He's not telling me.
hydrogen.
Okay.
Like,
Now we talked about the various belts.
Yeah, I don't know. It's like,
You have a belt there, we talked about them, we've actually drawn them on board before. D, E, F, G, I can't remember, 5 of them. As that electron goes somewhere, it releases energy. You can measure that as a color, and now you have a color spectrum. So with a spectrograph, we can see that frequency of hydrogen. But what you have to understand, it is not the frequency that we're going to find in astrophotography. On the inside there, you have the proton spinning around. It spins. Electron spins around.
I think
No,
it's
we're not talking about going around a circle, the orbit. We're talking about spinning of these individual elements. I shouldn't call it elements, but individual parts. There should be a word, but I can't think of it now. But anyway, if they're spinning the same, it's okay. But when one flips, because it wants to flip, or it got too hot, or it was hit too hard, it flips. When it flips, it gives off energy. That's the energy that you're going to find in astrophotography at that wavelength. So now you have two ways to start evaluating your universe. We can see it with our eyes, but we can't tell anything with our eyes. Everything looks the same. We can't tell how far the moon is, we can't tell how far Betelgeuse is, we can't tell how far Rigel is, we can't tell what, because they're all in depth, but we see it as two-dimensional. But it's not two-dimensional. So now the way we do that is with astrophotography. Okay. So, trying to think how to show that. Got a mental blank in what I want to say. Okay, so we moved from the physics, the mathematics of the energy coming out at a frequency at a light intensity. So hard to say. So, okay, draw the Earth down again. Just a circular Earth. No, not a circle. I'm sorry. Semicircle, I guess I should be saying. Just draw it on top of it. I want the whole thing.
what do you mean?
Like you're looking at the Earth. That's the Earth. Yeah, okay, that's good. Now, above us, put up there right below where your other drawing is Milky Way galaxy, and make that a long elongated eclipse. That's the Milky Way. Now above the Earth, draw a directional arrow, look. The Earth is rotating. Okay? Draw a line down the middle. Okay? Day on that right side. Day. Night. Okay? So now, in astrophotography, we want to look at the Milky Way. We want to look at a specific part of it. Just like if I want to look at the sign down the road there with a telescope or binoculars, okay? So, or if we want to look at Polaris, the North Star, or Betelgeuse at a specific star and a specific nebula. So draw a telescope on the daytime, no, on the Earth, up there, a telescope, looking up at the sun. Okay, now draw the sun. No, okay. Now draw another. I know, that's okay.
Where do you want me to put
This
it?
is hard to do without the slides, so draw another circle. Okay, sun, good. Sun big. Jupiter, put sun in there. Jupiter. These are the two main planets that we deal with, okay? Put out energy that affects the Earth. The moon puts out gravity that affects the Earth. So put the moon over the nighttime part. Down over there. So now, this is astronomy first. When I get up in the morning, I look and see, or when I go to bed, I look and see the moon come up here. Go down. Goes down in the west. So I'm looked out with my house. I can see it from upstairs coming up in the east, and at nighttime going down in the west. So when I got up for Holta, at sunup, in other words, astronomical sunrise, when I looked up, I saw Jupiter, I saw Orion with Betelgeuse and Rika, and then I saw, I can't remember the other planet over here, beautiful in the sky. So Betelgeuse is one that, generally speaking, it's easy to find, so you learn it to start with. Okay? So now if you think about what happened from the time I went to bed, that Earth rotated around. So I could see it, okay? But then it's gone. It's down underneath, or it's dark. So now I see things on this side when my telescope, interesting enough, what you have to get in your head, come here, run. The Earth goes this way, but this telescope is going to go over here. So at nighttime, put a telescope there. This is what confuses a lot of people. You didn't move, and the telescope didn't move. The Earth underneath you moved. So this is where teaching comes in, and a lot of people get very confused on how to put this all together in their brain, because you have three types of spherical geometry. You have nautical miles and terrestrial miles. and now we have celestial. So you try to combine this all at a low level, okay? But obviously the telescope will be looking at the moon at 12 o'clock. At noon, it'll be looking at the sun. Therefore, if you want a telescope to look at that sun for a long time, you have to make one very, very, very big. I'm talking about monster. That's when it was feeble, it fell apart because you can only keep it up so many years. So now what they've done is to change, and now they take and make an array. So connect the two telescopes. Down at the bottom, just draw a line connecting them. Okay, that's good. Oh wait, write down, wait, let me think. No, I don't want to get it wrong for the camera, so. But anyway, there's a short array and a long array. So if you know anything about resolution, the example would be we're getting into resolution where you can read a newspaper in New York or in California, a New York newspaper in New York by doing this array. So instead of having one big massive telescope that's going to fall apart in a few years, it'll be expensive, they put arrays up. And that's what we're going to do for the eclipse. For Jova, to look at Jupiter, not the sun. So what they're doing now is, let's say, wait, put USA over here above the telescope. Above the other telescope, put England. Now they connect these arrays by that long line. But you have to have a very precise clock to do it. You use what they call an atomic clock, which is absolute. So both of them have to run on a clock. If you've done anything, if you have a laptop, for example, and you let the battery go dead, and you don't use it for a year or two, before you can get it on the internet again, you have to set the clock. Everything has to be set the same as a clock. So the signal from one of those telescopes has to be the same as the signal for the other one to stack the images up on top of each other. Therefore, it's a lot cheaper and easier to get your friends to do it. We get our friends in England to make a decent sized budget telescope. We get our telescope in West Virginia up. We get friends in Germany to do it. And we connect them all together and say, everybody get on at 10 o'clock and get a signal. And then send it to somewhere. And then those people make a picture of the galaxy for us. Okay? There's another way to do this. The way we're going to do it, or amateurs do it. And this gets a little complicated. Okay. We're going to be going around. This galaxy is only going to be there certain days, certain times. So it'll maybe here from 12 midnight to 2 o'clock tonight. So we turn on our telescope, we record for 24 hours, and it picks up the galaxy only for those 2 hours. So again, this is the way people can do it with a cheap Yankee antenna. It doesn't have to be expensive. So it's called drift. We're going to drift around. We're going to look at it when it comes up, or when we come up. We are going to be going around. Tomorrow night we're going to come up again. So we got all this on a strip, just like an EKG. And we're going to have all these spectrums I talked about with the spectrograph and printed out with wavelengths. And then we can start, we talked about last week, the Milky Way. We can actually make a color picture of the Milky Way. We can tell where our stars are. We can tell where the Earth is in the Milky Way, our solar system. Most of this is done at universities, okay? You'll find very little of it done, generally speaking, in Texas, in certain places. McDonald University under University of Texas usually is done on mountaintops, the best place, okay? So there's only a few universities that have the power. A lot of this, Texas could become that, if they want, is being done in Arizona, because Arizona is dry, okay? El Paso, Texas advertises as being sunny for 340 days out of the year. So you don't want clouds, you don't want dust, okay? But they get dust from Sandia. So anyway, the bottom line is this here, down here, is what we call, you want to write that down? Astrophotography. So it's a combination of 1, photography, and 2, astronomy. Okay? And so far, this is our goal for Eclipse number 2. The Radio Club people have their goals. So far, it's more on what we talked about, the climate. They want to know what their radio waves are affecting the ionosphere, affecting an airplane transmission. The pilot says, I want to land, and all they get is static, and he needs to land because it's out of gas, he's in trouble. So the sun, as it comes out with what we call bursts, so we'll get more into the sun. I've got to get through your head the basics of the sun. Hydrogen, helium, deuterium, and all the elements. Specifically, the elements that we're concerned over is iron, okay, gold. Turn the page, Lisa. I'm going to try to blend some chemistry with this. Hydrogen is H.
I know.
He is helium. Iron is Fe. Gold is He. Chloride is Cl. Okay. These are all that you should know at this point by junior in high school. Okay. Copper is Cu. So now draw a line there. Now another part of elements that comes in as important is what we call, well, let's go back over here a minute. We'll call the rare earths. The rare earths are copper, gold, and silver. And those are classified as metals. Then comes inert elements. It's called inert elements. Those are what we use to radiate light, radiate energy. So, I was trying to think, neon, Ne. Can you think of any other ones? I was trying to think, I know them, but they're just not coming to me at this point. But we use these inner elements in photography. When you're doing things in photography, energy is heat. and light. So you've got to get rid of heat. Heat will come through as a white speck in astrophotography. It looks like a star. And this is why you take what is called darks. D-A-R-K-S. Darks. You take 10 darks, and that will be absolute black. And we've gone over that before, white balance and black balance and so on. So if you want a good lens, the kind Turkey was buying from France for the drones or for astrophotography, you might put an inert gas between the lenses. Lisa and I went over yesterday why you use oil on a microscope for oil immersion lens. You have to control the transfer of light. Well, an inert gas is like space. The minute you move above the ionosphere into space, there is no weight. Everything travels at the speed of light. So write that down, Lisa. Draw a line. This is an equation now. Draw a line underneath. Okay. The speed of light. This equation you must use because you're going to use it all the time. Easiest way to think about it is 300 meters per second. So your equation now, which we're not going to go over here, we'll do that in radio, is the equation is frequency versus the speed of light equals the distance, the wavelength. So that equation comes in all the time. So if you want something that doesn't change the light, you use an inert gas. So when you look at the moon, and they call it the blood moon, that is the gas in space, the dust, the vapor, making it look red. It is not red. When the moon gets high in the sky, it is white. So it didn't change color. It changed direction. So if you don't want that falsehood in your photography, then you have to find a way to get rid of those problems. And that's what neon gases do. So what this means to you is if you're going to get into this, even at an astronomy level, you've got to know what kind of camera to buy, and does it have a heating or cooling element in it? And two, how are they going to deal with the bad light, diffraction of red versus green? Are they going to use an inert gas? And if they do, it's going to cost more. So, okay. That's good. We'll wrap there.